Hey everyone! In this video I want to discuss an experiment about light detection with photomultipliers. In a separate video I discussed the principle of the photomultiplier and how this device operates as a single photon detector. If you have no idea what a photomultiplier is, it might be a good idea to watch that video first. Photomultipliers can detect the absorption of a single photon of energy, which in itself is a discrete event, but light also exhibits behavior that is typical of wave phenomena, for example interference and coherence, and the focus of this video will be on what coherence means for the detection of individual photons. In the past I've made several videos specifically on wave coherence, but I think it's still a good idea to give a very short summary about the main concepts of coherence in approximately 2 minutes. So, what is coherence when we talk about wave phenomena? In one sentence, it's a property that describes consistency and synchronicity. For waves there are basically two main types of coherence: temporal coherence, which is about consistency of a phenomenon over time, and spatial coherence, which is about synchronicity between what happens in different positions in space. And to illustrate this, I'll just show you a few examples. This is a point source that emits 2D waves in a plane with a single fixed frequency. In this case, the source emits waves uniformly in all directions. And if we take a point P1 somewhere random in the plane of the wave and look at the amplitude as a function of time, we observe that the signal is always the same. And that is because this wave only contains a single frequency. The same is true for any two points separated by space. If we ignore any differences in phase or amplitude, the waves in these 2 points are always in sync. So for this wave, we can state that it is coherent in both time and in space. Let's take a look at a completely different wave. Here, the wave source consists of multiple emitters, each continuously emitting at a slightly different frequency. And if we look at the amplitude of this wave pattern passing a particular point as a function of time, it could look something like this. It's clear that the wave patterns are not synchronized anymore if we compare them at different moments in time, not even if we were to add a fixed phase offset. And the same is true if we compare the waves that pass two different points in space. So this source is both temporally and spatially incoherent. The temporal incoherence is due to the fact that the source emits more than one frequency, and the spatial incoherence is caused by the fact that not all frequencies are emitted from a single point. Let me show you what I mean with the latter. If we put a reflector around this source with a tiny hole in it, the wave that exits the hole will also contain multiple frequencies, and this wave is incoherent in time, as is illustrated by the graph. But since all frequencies are now originating from the same point, suddenly there is a relationship present between the wave pattern at any 2 points, because apart from a time delay or phase shift and maybe an amplitude difference, the wave patterns that pass any 2 points are in essence identical, and therefore this point source is spatially coherent yet temporally incoherent. Now the previous examples were simple 2D waves in a plane, and the wave behavior in light or electromagnetic fields is in general quite a bit more complex, not only because it's a transverse wave in 3D space, but also because light has a property called polarization, which tells us something about the orientation of the field amplitudes in space. Nevertheless, when you want to describe light, the degree of coherence is a very important property to acknowledge, as hopefully will become clear in this video. In the experiment that follows, we'll use two fundamentally different light sources. One is a laser that emits spatially and temporally coherent light, and the other is a white light LED with a tiny pinhole in front of it emitting temporally incoherent light that is spatially coherent. The experiment involves doing single photon detections using two photomultipliers, and we will do this as shown in the following schematic. Here is the location of the light source used. The light from this source is collimated using a lens and then split into two separate beams of equal intensity in a beam splitter. And in each beam we will detect individual photons as a function of time. The signals from the photomultipliers consist of a series of small current pulses which we will register using a digital oscilloscope, and each of these pulses represents the absorption of a photon. Photomultipliers are extremely sensitive devices, and they need to be in order to detect the effects that light has on a single electron. So if we want to measure single photons in, for example, laser light, it's not a good idea to point the laser directly into the devices, because that will likely end their careers as light sensors immediately and permanently. So in order to avoid this, we need to attenuate the intensity of the light by quite a lot. In my case, about 8 orders of magnitude, or by 100 million. And by adding attenuation filters in the beam path, we can get the light intensity in a suitable range for single photon detection, even when using very intense light sources. Here is the measurement setup in real life, of course switched off because it's in the full light here. The light sources I just mentioned are actually mounted on the back of this black box and can easily be exchanged. The box itself contains a few apertures to block the majority of the light that's not used in the experiments. The box also contains a few slits in which you can place multiple neutral density filters to attenuate the light level of the source to a correct level. And these filters are all reflective attenuation filters, which means that part of the light is reflected and the other part is transmitted. To collimate the light into a beam, a lens can be mounted here on the front side of the box. And here you see the two sources together. To the left the green laser and to the right the white light LED source. The white light source is a standard white LED covered by a tin foil with a tiny pinhole in it. I estimate the pinhole to be around, let's say, 40 microns in diameter. The green laser has a wavelength of 520 nanometers, and at the power levels where the laser light becomes coherent, it's really quite bright. So, as mentioned earlier, this requires some serious attenuation of the intensity. So much about the light sources and the attenuation. The other parts of the setup are this 50% non-polarizing beam splitter, and then we have the two photomultipliers, each with their own electronics, which was also discussed in the separate video. The detector itself is inside a black anodized housing that shields most of the light, and basically the only way that light can currently reach the detector is by this pinhole at the front. For convenience, I added these little shutters, which can be used during alignment of the setup. Alignment requires a relatively high intensity because you need to see where the light beams are going. So this is done with the shutters closed, and we can open them up once the light source and the light in the room have been sufficiently attenuated. As suggested by viewers of the photomultiplier video, I stopped using the cardboard box and the towels to shield the setup from external light. Instead, I used a plastic container that was completely light-proofed with aluminum foil, tape and black spray paint. The box, by the way, is small enough to be placed inside a freezer to reduce thermal noise in the detectors. For the current experiment, that wasn't really necessary because the thermal noise was always less than 5% of the signal, a value which I considered acceptable. So all measurements were done at room temperature to avoid all the complications of additional cooling. Okay, let me show you what measuring light using a photomultiplier looks like. Basically, a measurement consists of many individual single photon detections for both detectors, and each detection is represented by a peak in the signal. So talking about single photon measurements sounds a bit funny here because these graphs look awfully crowded with photon detections, but that is mostly because the time scale is heavily compressed here. If we stop detection for a second and zoom in on the individual detections, we observe that even at the highest intensity levels used, peaks are spaced far apart and in fact very rarely overlap. Notice also that there's quite a lot of variation in the peak height. I'm not an expert on this, but my guess is that this is because of a large spread in the amplification gain between individual photon detections. So the actual measurement consists of collecting a lot of photon events from both detectors simultaneously, and we'll repeat this experiment for a few different light intensities and for the two different light sources, so the coherent laser light and the incoherent white light. At each intensity, we'll record peaks over a total time interval of 10 milliseconds, multiple times, and in my case, each measurement contains 1 million data points, which brings the time resolution to 10 nanoseconds. And for now, this is more than sufficient to resolve individual photon signals. Now, the problem with presenting these experiments here is that they're not very spectacular to watch, because they are performed in complete darkness with very, very dim light sources. So here you see an actual experiment as it is being performed. Yep. The most exciting moments are when you have to open the box to exchange a filter and everything else is actually happening on the screen of the oscilloscope and in signal processing. So what I want to do now is quickly talk about the aim of the experiment, then I'll show you the result, and after that we'll talk about the deeper meaning of the experiment in quite some detail. Okay, so if you look at the signals of coherent and incoherent light, you really don't notice any difference when you examine how they're, for example, spaced. But there actually is a difference, and to bring out that difference we need to find the pulses that overlap in the two detector signals, so photon detections that are simultaneous between the two detectors. Because of the low light intensity, these occurrences are pretty rare, so it's a bit like searching for a needle in a haystack. But a very simple method to find simultaneous peaks is to do signal multiplication, because only in the case of pulses overlapping we find a significant value in the multiplication result. Signal multiplication is actually a very common functionality featured in many oscilloscopes, even cheap ones, and can basically be done in real time. And what we can do now is count the number of pulses in the multiplication graph that have a certain minimum height and plot their number as a function of the overall pulse density in the signals. Now, counting pulses is a tedious process, especially if there are like a few thousand of them per measurement, so I used an evaluation version of a program called SIGView for that. I'll leave a link in the video description. Also, the experiments require a lot of averaging over many measurements at different intensity levels, but what I'll do is just show you the result. Here is what the number of coincident pulses as a function of the average pulse density looks like for coherent laser light. We observe what appears to be some sort of linear dependency between coincident pulses and pulse density. Now let me show you the result of the same experiment with incoherent white light. We can observe a similar dependency between pulse density and pulse overlap, but it also shows that in this case the number of times that two peaks overlap is significantly higher at a specific pulse density, and that is a bit unexpected, I guess, because it would mean that in the case of incoherent radiation, detections must somehow be more correlated. But why would they be? Now, before we talk about that, let me emphasize that this experiment is not intended as scientific proof or anything. It's just a brief demonstration of a phenomenon that's better known as photon bunching. It's the effect that for incoherent radiation, photons seem to be on average more bunched together in time, compared to the case of coherent radiation, where photons are detected randomly in time. And this is illustrated in the schematic, where each dot represents a single photon detection. There's also an effect called anti-bunching, which occurs with single photon emitters. I felt I needed to mention this, but I'll leave this effect out of the picture here and focus purely on bunching. Before I dive deeper into the explanation of this phenomenon, we need to be on the same page about what a photon is. I guess the most common misconception about photons is that they are some sort of small particles that together make up light. And many people I've talked to imagine them to be little localized discrete blobs of wave energy that travel from where they are emitted to where they are detected. And this view is completely understandable because everywhere you look, it's how photons are presented. Not just on YouTube. If you look on Wikipedia, you'll find that the opening paragraph contains 3 references to the photon being a particle. A photon is an elementary particle. It's a massless particle that moves at the speed of light, and on top of that it's apparently also a boson particle. Now, a photon is not a particle. What we measure when we detect a photon is an interaction. The absorption of a photon is the exchange of a small discrete amount of energy, and in the case of the photomultiplier, the transfer of that energy to an electron. And that's actually all we measure. So even from the viewpoint of measurement itself, detecting a photon is not about detecting a particle of some sort, it's about detecting an interaction. So according to Wikipedia, the photon is a boson particle. And if you look up bosons in the standard model of elementary particles, you'll find that they're classified as interactions. So I guess for convenience, particle physicists call everything that is quantized a particle. But from the viewpoint of understanding the behavior of photon detection, this is very confusing. Let me use an analogy to explain. A slap in the face is an interaction involving a quantized amount of energy. The energy is exchanged between a hand and a head. In the analogy with light interaction, the head is the electron, the slap is the photon, and the hand is the field. But in the case of the slap, it's clear that a slap is not the hand itself. It's the energy transferred during contact. And for a photon, it's the same thing. The photon is not the field, but the energy transferred between field and matter. By the way, not all interactions between a field and charged particles require quantization. Phenomena like refraction and reflection can best be explained from classical principles without any need for energy or field quantization. However, when the energy states of an electron become quantized, for example, because of electrostatic confinement in space near a positively charged nucleus, any absorption and emission phenomena must involve the exchange of discrete amounts of energy. And not only can these amounts of energy only be delivered by a specific frequency of radiation, the process of transfer itself becomes inherently probabilistic and dependent on field intensity. So let's focus now on the relationship between field amplitude, intensity, and photon probability. In classical electrodynamics, the intensity of electromagnetic radiation is proportional to the field amplitude squared. A field having 2 times the amplitude has 4 times the intensity. So the relation between field strength and intensity is pretty straightforward. The other symbols in the formula are actually just properties of the vacuum and are constants, like the permittivity and the speed of light in free space. Now, radiative intensity is the amount of energy that passes through a unit of surface per unit of time. So it could, for example, have a value of, say, 10 microjoules per square meter per second. Since energy absorption is a process that involves exchange via discrete quanta of energy, it follows directly that the number of transactions required to do this per second is proportional to the intensity of the radiation. But because these transactions occur unpredictably, the time and location at which they occur are governed by probability. Now, since the number of interactions per unit of time and area are a measure of probability, we can say that the probability of interaction is proportional to intensity. In practice, this means that energy exchange to an electron can happen at any moment. It's just more likely to happen more frequently if the field intensity is higher. So in summary, we can state that probability is proportional to intensity and intensity is proportional to the field amplitude squared. So to illustrate how these relationships work in practice for wave phenomena, let's again revert to a few 2D simulations. Here is a source that emits wave energy continuously at one particular frequency, and using classical wave mechanics we can calculate the intensity of this wave from the amplitude as a function of position. Some of the wave passes this line here, and if we plot the wave intensity as a function of position on the line, we find this curve. Now if we take another wave source next to the original source and look at the intensity at the line, we observe the same kind of energy distribution, just slightly displaced. If the two sources are coherent, switching them on together at the same time does not result in an intensity distribution that is the sum of both intensities. Instead, we observe a wave interference pattern, which is the result of amplitudes adding up linearly. Where they add up constructively, it will indeed locally result in an intensity that is 4 times as high as the uniform intensity of an individual source. But you also observe areas where the intensity is very low because of destructive interference. So the total amount of energy through all of space is equal to that emitted by the two sources. It's just redistributed because of wave interference. Now at this point it's good to realize that this is an example of a classical wave. Experimentally, we do not observe this intensity curve directly, but we observe a time average of many discrete energy interactions. The individual interactions are basically the result of a local field intensity which, as we've seen, governs photon probability. And what this effectively means is that if you make the intensity very low, individual detection events will become very sparse, but each of them will still follow the probability distribution in space resulting from the local field intensity. And, at least to me, that is the underlying reason why we can observe interference even one single photon detection at a time. It's not because the photons are particles that behave like waves, but because they are discrete energy transactions whose probability is dictated by a field intensity distribution. Here is a quick example of two incoherent broadband wave sources. The simulation shows that in this case there's just as much interference going on, not just spatially but also temporally. However, if this were to represent broadband visible light, it would mean that these temporal intensity variations only extend over a few wavelengths, meaning that they occur in the femtosecond timescale. And if you could observe the intensity on this timescale, you'd find that the intensity varies widely over time and space. On the other hand, a time average intensity shows no sign of an interference pattern. Let's now consider what happens in our setup with temporally coherent and incoherent light. Here are two detectors that are detecting the field resulting from a source that is completely coherent and has constant amplitude. This type of field would be representative for a stable attenuated laser. Based on field amplitude, both detectors would now have an equal probability of detecting a photon, and that probability would be constant over time due to the absence of temporal interference. So based on intensity, photon detections would in this case be completely random in time because the detection probability is constant in time. Here are the same two detectors listening in on a temporally incoherent signal that is spatially coherent. In this case, the intensity is non-uniform in time, which leads to temporal probability variations. However, these variations are identical for both detectors. To illustrate this, I have plotted the intensity in the currently displayed beams as a function of the position along the two lines indicated. As expected, there is an exact intensity correlation, which means that there's also a probability correlation between detector 1 and 2, and the net effect of this is that there is a somewhat higher probability of making two simultaneous detections in incoherent radiation compared to coherent radiation at the same average detection intensity. And that is the more intuitive explanation behind the effect that we observe in the experiment. More quantitatively, correlation between intensities can be described by what is known as the second order correlation function G2. This function quantifies the correlation between intensity variations as a function of a time difference tau. So what we do in this function is multiply the intensity at a time t0 with the intensity at a different time t0 plus tau. And we normalize this value by dividing it by the intensity at t0 squared. The denominator is basically a normalization factor to correct for the overall average intensity. But the value in the numerator is indicative of how much and how fast intensity variations occur over time on average. And that is what the brackets indicate, that these are a time average over many values of t0 that describe how intensity variations fluctuate in time. Now, even if you literally know the intensity values at t0 and t0 plus tau, I guess understanding this formula isn't really straightforward. But in measurements with single photons, things are even more complex. And that's because we're not measuring intensity variations directly, but a pulse pattern, which is the probabilistic result of intensity. And from, for example, this pulse pattern here, it would be very hard to say whether the intensity variations in time look something like this or like this. However, there is a way, and that is by statistical evaluation of the separation times between pulse pairs detected at t0 and t0 plus tau. Now, I agree, this all looks pretty complex, but in practice it's not that difficult to do. If you have two detector signals, a way to measure second order correlation is to take a specific pulse at detector 1, call the time of detection t0, and define a time range delta t in which we will search for any correlation with the pulses of detector 2. We determine the time differences tau between the initial pulse and the pulses observed at the other detector and collect all the values found for tau into a set of discrete bins. We then repeat this process for every detection made at detector 1, and if we do this for sufficient pulses, we end up with a histogram containing a statistical distribution of time differences and how frequent they occur. And what this distribution defines is the probability of finding two detections as a function of time differences between two pulses. If pulses are truly random, there will be no correlation between detections from both detectors within the time interval. So the histogram will return a flat distribution as a function of tau. However, if photon detections are more likely to occur close to each other, we will find a bump around t0. And this bump is indicative for photon bunching, because statistically speaking, photons are detected closer to each other in time than you would expect based on true randomness. Measurements involving photon bunching find a real-life application in what is called stellar intensity interferometry, because it can be used to determine the angular diameter of stars, so the ratio between the real diameter and its distance to Earth. The method is based on the Hanbury Brown Twiss effect, named in honor of the inventors, Robert Hanbury Brown and Richard Twiss. The essence is that you can take two very modest telescopes placed some distance apart. You point them at the same star and accurately time the photons you measure, compare the signals and establish the degree of correlation. You repeat this measurement for a few different distances between telescopes and optionally for a few different wavelengths. And from the resulting data, you can now in principle derive the ratio between distance and diameter of a star. When Hanbury Brown Twiss proposed this measurement method, fellow astronomers were quite skeptical about the feasibility, but the skeptics were quickly silenced by the solid experimental evidence that the two were able to show. The underlying math is pretty complicated, but the principle behind the idea is simple. For incoherent light sources, a relationship can theoretically be derived between the diameter of the light source d, its distance r, a wavelength lambda, and what is called the area of coherence, assigned here as AC. And the relationship between these four variables is described in this formula. Now, inside the area of coherence, light has become spatially coherent to a large degree. So if we return to the measurement setup of the telescopes, if two detectors are within the same area of coherence, we'll find a correlation between photon detections, whereas if the two are moved outside each other's area of coherence, correlation will disappear. So by determining the area of coherence at a particular wavelength, we can effectively calculate the ratio between a star's diameter and its distance. Given the previous about the second order correlation function, I was curious if I could maybe get some more information about bunching of photons from the data that I had gathered. Basically, the timing data of the photon detections that I already had would allow me to perform a second order correlation analysis on them, but unfortunately I could not find any simple software online that could do this for me. So I decided to write a little app myself using the free version of Microsoft Visual Studio. Now, watching software being explained on screen is generally not very fascinating, but the way this app works is that it can import two separate data files that contain the peak data of the two detectors that were collected simultaneously. And after the data are loaded, you can take a peek at the data that was imported, which shows you the data points. Now, each point consists of a time of measurement and a peak intensity. And what the software can do now is calculate a second order correlation distribution from the timing data and display the distribution as a time difference histogram. And I guess this might look familiar to you given the previous discussion. Now, this particular histogram is showing the correlation function between detectors in case of coherent radiation, actually without any normalization. But the result is exactly what we expect, a uniform distribution as a function of time differences between pulses, which is representative of a random distribution in pulse probability. So it's exactly what we want. Next, I tried to find the presence of correlation in files containing incoherent radiation data to find that bump indicating the effect of bunching. And this is where I actually completely failed. Could not find any significant bump, not even by merging multiple measurements into accumulative histograms. So that was a bit puzzling. At this point, the most logical thing for me to do was to check for bugs in the code, because no software is error-free, especially mine. So to check whether the software was working correctly, I used signals that contain a form of artificial bunching. By using modulated light, you can make sure that some degree of time correlation between photons must exist. And here you see an example of a signal that was deliberately bunched. By zooming in on the data, you can see the individual photon bunches as groups of photons in time, And if we create a histogram from this, the result displays very clear correlation, both within individual bunches as well as between separate bunches. So the software worked just fine, and the absence of any bunching in the actual signals was probably not a software error. It took me a sleepless night to realize that the reason was probably related to the maximum time resolution of the measurements, which is 10 nanoseconds per data point. Since the phase correlation time of light is directly related to coherence time, we can calculate its value from the spectral bandwidth. For broadband white light in the visible range, the spectrum of frequencies is centered around a wavelength of 550 nanometers. Using a bandwidth of say 200 nanometers, which in this case is equivalent to 200 terahertz, you can calculate that the coherence time should be in the order of 5 femtoseconds. And this means that we can basically only observe the loss of correlation using data that has comparable time resolution. And with a time resolution of 10 nanoseconds, that would be very difficult, if not impossible. So I decided to post a preview of this video on Patreon with this conclusion. But when one of my patrons asked why it was still possible to observe the effect of bunching in the original measurement, I didn't really have an answer to that. The only thing I could come up with was that it had something to do with selecting the data based on direct overlap of peaks. And that is when it hit me. So far, I had been using bin sizes that were quite large compared to the time resolution of the data. The reason being that if the bins are too small, there are very few data points, which results in sort of a nonsense histogram. But if you have bins that are large with respect to the width of the bump, the effect of the bump will become insignificant within a bin. So I wondered what would happen if I were to make the bins as narrow as the distance between two data points and use all the data I had. Well, let me show you. It's quite surprising. Here's what happens with coherent light. In the accumulative histogram here we do not notice anything peculiar. It looks like a constant signal, just very noisy. And here's a demonstration of collecting histograms for incoherent white light. Focus on what happens in the central bin when we start accumulating. We observe how the central bin grows faster than the rest, and the reason is that the bump we're looking for is completely contained within this central bin. But with the bin now being very narrow, the bump has become statistically significant within the bin. So this is our bump, just not as detailed as I had hoped for. And it can only be resolved with the data if we take the time resolution used in our measurements as the histogram bin size. Okay, I want to end this already long presentation here. Hope it gave you some new insights on single photon detection, or even about what a photon is. If you have any questions or remarks, please leave a comment, especially of course if you passionately disagree. Thanks for watching.